Hello and welcome to the Point Blank Show. My name is Abhishek. Mathematics is part of our daily lives more than we think or know. For many millennia, men and women from across the world have made groundbreaking discoveries. Maths underpins pretty much everything around us. In The Secret Lives of Numbers, a global history of mathematics and its unsung trailblazers, Kitagawa and Timothy Revell bring us fascinating stories from bygone eras that may even make you fall in love with the subject. And what is more, the book has just been shortlisted for the coveted British Academy Book Prize of 2024. Thanks, Kate and Timothy, for joining in, and congratulations.
Oh, thank you very much for having us.
Thank you very much for having us.
Celebrations are in order for this big news, and here it is.
Thank you very much, and thanks for having us today.
We're recording this for the listeners 24 hours after this news came out. I've got a little something for you, and I don't know how this works. Yeah, there it is. So, and you've got some very stiff competition, but I'll be rooting for you. More importantly, the book, The Secret Lives of Numbers, for somebody who doesn't know much about maths, for somebody who doesn't know or understand much of maths, I quite enjoyed it. It speaks to the common man. I don't know, how was it for you guys? Did you grow up loving numbers, as I would imagine? Not so much for me. I was on the fence. I did well. I didn't fail the subject, but it wasn't in my top two. How was it for you?
I always love numbers, so I'm so happy that our title has the numbers in it. But, it's just really nice to have a grand narrative of global history, and I'm really happy to hear that reader like you quite, enjoyed reading this book. So yes, thank you.
And how was it for you?
For me, I've always loved mathematics. Certainly at school, as you kind of get exposed to more mathematics, I became more and more interested in it. So around A-level time in the UK, which is sort of 16, 17, 18 years old, you start to get a bit more interesting mathematics, and that was when I first started reading about mathematics beyond school and came into contact with lots of authors who have written about mathematics, like Simon Singh and Ian Stewart and those kind of people who've done a really good job at kind of popularizing mathematics. And it was then that I got interested in the history of mathematics as well. And then, I went off and did a degree, and just like Kate, we both got backgrounds in mathematics. But I guess it was when we met that we started thinking about, well, could we write a history of mathematics that would be accessible to a really broad audience? Like, the history of mathematics is absolutely fascinating, even if you're not a kind of nerd who's really interested in the equations and the numbers. And so that's what we set out to do with this book.
And one of the things that is striking way early in the book is you need to use your imagination to work with maths. For the layman, it is quite binary, meaning it's either yes or no, you've got numbers. How is imagination tied to mathematics?
I think the mathematics we're used to is you get given a very specific problem, and then you've learnt already a specific set of steps that you need to undergo to answer that question. And that's often, you plug the numbers into an equation, or you follow a very simple algorithm, and that gets you the answer for what the area of this triangle is, or something like that. And that's not very imaginative. That's like working like a robot, very step by step. And calculators and machines are really good at that. But that's not what most mathematics is like. That's not what most research mathematics is like. Normally, you've got a really big problem. You don't know what you need to do to answer that problem. And also, the mathematics you need to answer that problem hasn't yet been invented or discovered. And that's a thing people discuss in the world of mathematics, whether it's invented or discovered. But either way, we don't know what the fundamental things you need are to answer that question. And so you're really kind of like walking in the dark, trying to understand, where do I go to answer this problem? And for people, this can be decades and decades of work just to answer a single question. And that involves an extreme amount of creativity. Just like in art, where you're building on other people's work and taking inspiration, that's what mathematicians do. But until you actually hit upon the right route to answer a problem, it's all about creativity and just trying to understand what it is you're actually trying to solve.
And some of the stories that you've covered in the book is something that should be part of school trivia, if not the main subject itself. Did it surprise you when you both sat together over a cup of tea, whenever that was, a few months or a couple of years ago, that you wanted to do this book? Because there wasn't much out there that could be consumed by someone sipping a cup of coffee in Mumbai or New York or Tokyo or wherever.
Yeah, it was like amazing to start the project, and we thought that was really easy to write up from some major events of mathematics in the world, even while doing the research, that there's just so many things that we wanted to include, and then we really wanted to communicate with this imagination. Things really becomes interesting after maybe having one cup of tea we did not know, maybe another time that we met up we just didn't even know, but the third time we were sure that this will really take a lot more than imagined from the beginning. But what's really nice to have a writing partner, we wrote together as a co-author, and we could talk about things together, and we could structure things together, and I really enjoyed learning so much from Tim. So it has been great tea time all along for how many years now, Tim?
It's been a few, and likewise I learned so much from you. But I think did we first start this 2019 2018 maybe?
Oh,
it's been
yes.
a long time coming.
Amazing. And one thing though, in your secondary research as well, when you decided to write about the unsung heroes and heroines of the yesteryears and different centuries, there isn't much of it already out there, and that itself is telling. Why do you think that is?
It's a good question. I mean, there's a long history of the people who are writing history being very biased in some of the things that they write, focusing on the stories that they want to tell. And in mathematics, the real dominant story often has been that a few thousand years ago, Greek mathematicians sat around, worked out mathematics, and that's what we've been living with ever since. But I think the thing that just doesn't fit that narrative at all, and also doesn't fit people's ideas of what mathematics should be like, is that it's not a straight line, and it's not been a straight line at all. Mathematics, the history of mathematics, is actually extremely chaotic, convoluted. Sometimes people go down dead alleys. Sometimes something is discovered or invented only to be forgotten again and then reinvented many years later. There's been some, between very distinct civilizations, there's been some communication and ideas passed around. Sometimes they evolve, sometimes they don't. And so to kind of point to any one civilization and say, this is where these ideas definitely originate from and slowly make their way through into modern mathematics is really, really hard to do. And I think a lot of certainly Western historians have spent a lot of time on the Greeks, thinking about how those ancient ideas fit in with the ideas that were then rediscovered in the Renaissance. But it's far more complicated than that, but in a beautiful way. I think the thing we've discovered throughout writing this book is that the origins of mathematics are chaotic, but in a way that is just fascinating and really wonderful, I think.
And talking about origins of mathematics itself, when you started digging into the subject and where it all began, how did you know where to stop? Modern mathematics, or the maths that we know today, is not prehistoric.
Right. So it's interesting to pick the origin. So instead, we have many origins of many things. So sometimes about numbers, sometimes about counting the time, and also counting itself. So we try to have different beginnings, in different chapters. So you captured it well, saying that how do we stop chasing after how old we go and everything. So first thing was probably about some sort of evidence that we are looking for. So we have a chapter about counting. And of course, counting may have longer history, but without some sort of artifacts or something that we can see, we can't really be saying, exactly when, we see the evidence, right? So that's where we stopped. So the counting wise, we had those bones, as evidence, and also some calculators, so say some kind of calculating device that goes back to abacus and, more older style of counting tools. So we went for some materials that indicates, the usage of such. But also writing too, numbers and all the things that changes many ways. And it was really interesting, journey to wrap things up and then trying to show the multiple roots of mathematics.
One of the oldest examples we have of mathematics is this thing called the Ishango bone, which is this bone that was found in the Democratic Republic of the Congo about 20... Its origins are from about 20,000 years ago. It's obviously found much more recently than that. And one of the interesting things about it is it's got these notches on it that suggest some sort of counting. Kate's just holding up a picture of each side of this Ishango bone.
Yes.
And the notches, there are 60 of them, but they're clearly in kind of demarked into three separate groups, each of which are prime numbers. And that in itself is kind of just this, like, is that an amazing coincidence? Could it be that it was actually got nothing to do with counting at all, and it's just these notches have been put there and it was a tool used and that was helpful to have grip on it by having these marks? Or could it be that 60, which is a number that we hold quite a lot of in mathematics as being an important one, it's super divisible, that's why we use it for time. Could it be that they had some understanding of a number system, that 60 was the basis of it, and they understood prime numbers, at least in some way, maybe not in the way we understand them today, but maybe that way. And so that's 20,000 years ago, and that's basically the earliest origins we know of mathematics. But if you compare that to how long Homo sapiens have been around, which is hundreds of thousands of years, it's really distinct. So like Kate alluded to, it could be that number systems were much more verbal and there wouldn't be any evidence of those today, but it certainly seems like humans have been around a lot longer than mathematics, even though for us today it feels like they're almost indivisible, humans and mathematics.
And another theme in the book is mathematicians learn from each other, and they would learn from discoveries of hundreds of years ago, and they keep questioning the status quo. I think one of the chapters somewhere you talk about Johannes Kepler. He was merely, quote unquote, an assistant to a mathematician, and he was, I think, told to figure out the position of Mars in the solar system or some such, and he made a startling discovery by, I would not say binning his mentor's work, but probably saying that, hey, you were wrong, this could be a possibility. So that's a refrain in the book then.
Yes, I mean, like about Kepler too, but also other people we decided to include. They are sometimes very undervalued, but they had amazing insights. And, those people sometimes had, different sort of, tales or saying about or secondary stories about them. But at the end of the day, it's really nice to, go back to the very primary sources and then try to figure them out, who actually really thought about it first could be, somewhere else, or, could be someone else, and so on. So we really washed off all the charts of, when it was started and then how it was started. So the stories that we had in mind, we had to wash them off and then try to locate and then put our own timelines. So that was a great exercise that we went through all the way. And it just doesn't matter how, which century, but we always have to reconfigure our minds to try to accommodate the great facts about, someone who's usually considered as minor figure. So one person you mentioned was Kepler, but also another, many examples, because this title, as the title says, it's all about unsung trailblazers. So we have many people from different parts of the world too. And I was really quite fascinated about those figures. They have own history and also life stories, and they have many different ways to express. So sometimes it could be the sketches, and it could be some sort of time counting machines. So there are many ways contributed, and then I thought that's why this book is really more rich than what we knew from the time that we thought about the history of math as is. So Tim, do you have a favorite person that you like to talk to when it comes to
I don't know a favorite person, but this idea that mathematicians learn from themselves is, as you say, it's a really common theme in the book, especially in early mathematics. Really, the job of the mathematician wasn't quite the same job that we would think of today. Mathematicians would spend a lot of time effectively studying and copying texts that already existed. And then the mark of a really excellent mathematician was one who improved things, improved the explanations, or added to those texts. It wasn't that people were writing completely new treatises very often. One name that springs to mind who was involved in this was an Indian mathematician who maybe we'll come to in a bit, called Aryabhata. And one of the things he did in his book was he came up with the idea that the reason that the way that the stars move in the sky is because the Earth rotates. And this is obviously an idea that springs up later and was very controversial at the time. And you think, okay, well, maybe this is the point. This is the point we realise that it's not the Earth rotating around the sun. Actually, the Earth rotates, and that is partly what explains the movement of the stars. But then the subsequent mathematicians who copied his work, they just ignored this part. They thought, this can't be true. This seems so unlikely, so we're just going to ignore this. So again, in this kind of chaotic history of mathematics, it's not always that like suddenly you hit upon the correct idea and then it spreads sometimes. And he wasn't even the first person to suggest this, but sometimes people suggest these ideas and they don't quite take off. And that's something we see a lot throughout the history of mathematics.
And it's fiercely competitive too, isn't it? Calculus, for example, which we take for granted for everything around us, whether it is calculations of how rocket engines work or even filling a water tank, a calculus might be used there. And or in tennis, when they try and predict the trajectory of the serve, if it's on the line or outside the lines, it's all calculus. Then Newton, Leibniz, if I'm pronouncing his name correctly, from Germany, were all competing with each other, and Newton was particularly a bit of a taunt master in the whole thing.
It's a really infamous story in the world of mathematics, this kind of battle between Newton and Leibniz. So Newton was this English mathematician, extremely famous still to this day, and Leibniz was also a pretty well-standing mathematician, but a bit less famous and certainly not the darling of English mathematics in the way that Isaac Newton was. And both of them had hit upon the ideas of calculus. And there was this very public kind of battle for who had got there first, who should be declared the inventor of calculus. And I'll come to in a sec that actually neither of them is the right answer. But there was this moment where Isaac Newton effectively said, look, we need to come up with a solution to this. Who got here first? We can't both claim a superiority here, so we should get the Royal Institution in London. They can decide who got there first. Royal Institution has a think about it, writes a report and says, okay, Newton got there first. But who was the head of the Royal Institution? Of course, it was Isaac Newton. So it was hardly an unbiased answer. But actually, this was all happening in the 18th century. But in the 14th century was a mathematician called Madhava, who was at this Kerala school that you mentioned. And there he had a whole team of mathematicians who were working on ideas that show those fundamentals of calculus. It's not the same calculus that Newton was working on, nor quite the same calculus that Leibniz was working on. But it shows that early school understood the basic origins. And one of the analogies we write about in the book is that Thomas Edison, when he was inventing the light bulb, they don't look like the LED light bulbs we have today. They use and even some of his first light bulbs were extremely terrible. They did not fully function, but we credit him as certainly one of the inventors of the light bulbs we have today. And in that same way, Madhava in the Kerala school holds that role. Kate, did you want to add more to that?
So our story is not definite yet, that we would like to have more sources coming up in the future and then try to make this story even more rich. So we certainly hope that this is the beginning of this debate, in the 21st century. And then, hopefully that there will be more candidates of the winner to the story.
Yeah, and one of the things that blew my mind, and I want to ask you, what is your story? When I ask you what blew your mind, mine was when you write in 1550 BC, ancient Egyptians, that's where you tracked or traced the oldest surviving mathematics textbook. They calculated the slope of the pyramid from its height and width. So they had practical applications, and this is going way back, which I thought was quite tremendous.
Yeah.
Yeah.
Many things to choose from, Tim. Would you like to go first?
I might need a moment to think about that, if you've got one that's off the top of your head.
I think my favorite moments are two, actually. So those are the moments of synthesis. The world history or the global history, we have to see the point where some group of people will assess which sort of regional mathematics are more superior, right? So the first moment was this something called the House of Wisdom. That's in current day Baghdad, but it doesn't exist anymore. So it used to be a big library, And there were scientists and translators all together and collecting materials from neighboring areas. So there are many different languages, and they gather things in this house. And that became a powerhouse because they have collected all the available, most up-to-date knowledge. And they will have to examine like which is better or which is more efficient and so on. So this House of Wisdom was my favorite place to write about. And another time at the emperor's court in China, and that was the time that Kanji emperor was in charge. And there was a time where Western mathematics and Chinese mathematics were placed on the same table, and they tried to assess which one's more superior. So that was a time that many scientists and people who were knowledgeable, they will all gather and then try to do mathematics for the emperor. And that was really nice to see the developments. And at the end of the day, they're really fair, and they try to collect more data to prove which one's superior and so on. So those exercises, it's very much cultural, and we have not really understood because we thought like mathematics is more linear than that. So those two places where we found, many interesting things happening, like synthesis happening in the world. And I just can't forget about, how amazing it was to do, write about those places.
This culture is another element that keeps propping up, doesn't it? For example, zero, which obviously was a huge breakthrough in mathematics, but it had a bad rep, was it? Where some cultures, they had a distaste for it, they didn't like it, or for whatever reason. What was that all about?
Zero has this amazing origin story that I think for us today, it feels like it should be, one of the first numbers you learn. It's really foundational. You can't build a number system without zero. But for actually most of the history of mathematics, zero did not really exist. And part of that is absolutely a cultural thing. There's this interesting experiment we mention in the book that just kind of highlights why it's actually not that intuitive a number. And it involves showing 4-year-olds boxes with different numbers of dots in them. There's either 0, 1, 2, 4 or 8 dots in each box. And the 4-year-olds have got to decide which out of 2 boxes has got the fewest number of dots in it. And when the numbers are 1, 2, 4 or 8, the 4-year-olds can do it pretty well. With about 3/4 of the time they get it correct, which is way better than chance. But as soon as there's a box that's got 0 dots in it, the 4-year-olds, they can't do it anymore. They had no better than chance at picking the box with the fewest number of dots in it. And I think that just gives us a sense of why zero might have taken so long to develop, because it's less intuitive than the other numbers. And the kind of earliest origins of zero, probably with the Maya mathematicians in kind of South and Central America. They're one of the first people to have a symbol that represents zero. It's this kind of shell type symbol. And then a few other civilizations also developed their own symbols for zero. But it's really quite a lot later that we start to understand the number zero as a number in itself. And that comes around the kind of 6th and 7th centuries with a mathematician called Brahmagupta in India. And he's the first person who really takes zero, which at this point is being denoted as a kind of dot, sometimes a bit of a circular kind of dot, so looking like the zero that we know. And he actually says, no, this isn't just a thing we can use as a placeholder, a thing that helps us differentiate between the numbers 101 and 1001. It's also a number in itself that can be added, it can be multiplied, you can also divide by it, which is kind of what calculus is, and Brahmagupta doesn't quite get the right way to divide it, but he even suggests that that is a possibility. And off the back of that, zero becomes this fully fledged number. But as you say, not everyone's willing to accept it. The kind of Catholics in Europe years later are unwilling to accept zero. They think it's got some kind of evil connotation. For a while in Florence, it's completely banned. The idea of banning a number, it seems so unreal to us today. But for them, it just doesn't fit their ideas of what a number should be. And we kind of muse in the book, well, why is it that some cultures thought, no, zero is not right. So there's something wrong with zero. It's a bit off. It's a bit iffy. But in Brahmagupta's case, he was able to recognize the importance of it. And we speculate that it could have had something to do with the culture at the time, that there was a kind of Buddhist idea that from nothingness is where the infinitude of the world and the universe comes from. And so nothingness, there was quite a few different words that related to nothing. and just embedded in the culture was an importance of nothing and therefore zero. And therefore, they were starting from a kind of cultural point that allowed them to recognize the importance of zero as a number. And that's a really important theme in the book, that mathematics isn't just abstract logic, it is also cultural. And here we really see that without that cultural understanding, you also wouldn't have that mathematical understanding as well.
Also, personally, that last April, I went to Cambodia, and in the Museum of Currency, there was a place that they started to put zero as a character, and we wrote about it in the book. But seeing it for real was like really amazing. So I hope that some places, like say Indian zero or like some other places, have old zeros. I hope that you will encounter them sometimes to really feel the excitement and then really feel this was like 1,000 years ago, and they tried to use it. Not just a placeholder, but now you're becoming zero as like something that you can calculate, like, multiplication by zero or divided by zero and everything. So zero is quite a great number. It was like late appearance that really makes us feel like, this is a special number. So I hope you discover more in India as well.
Yeah, and in India, China, these countries, you've given enough text to them in the book. I think China doesn't get enough credit, is what I take away from the book. And oftentimes, after a discovery is made, you trace back and you find that some Chinese bloke has done it, or at least some semblance of it.
That's right. So even the first female figure that we looked for, we know about Greek history of mathematics, and then maybe Hypatia was one of the woman, known as great mathematician, teacher, and so on. But the Chinese side, as you said, where to look for and try to read materials that we can get access to. And there was more older age, like going back to ancient. And there was a woman called Ban Cao. She was a historian, so a writer, and also mathematician. And her figure showed up, and then we're very thrilled to introduce figures like her, and also more elements from Chinese mathematics that we try to have fair sort of treatment of all the cultures and all other great stories that we have not been hearing a lot about.
Yeah, China was one element for me that I really didn't have a good understanding of Chinese mathematics before we embarked on this book, and was just utterly mesmerized by how incredible the mathematics in China was. And it's actually, when you look at some of the earliest mathematics we know of, China is one of the first places where we actually come to know mathematicians by their names. In kind of early Babylonian mathematics or early Mayan mathematics, it's mostly scribes who are mathematicians, and we don't know their names. We've got some, scribbles on clay tablets, but we don't actually know who was behind them. But in China, we start to learn of some of these people. And one of them, by the name of Lu Wei, he was involved in this book called The 9 Chapters of the Mathematical Art, which was one of these books that got passed down and people improved on it. And he was one of those people who later on kind of added to it, annotated it, and tweaked it. And in his version of the 9 Chapters of the Mathematical Art, he does a whole bunch of things. One of them, he adds the best estimate of pi yet that was known anywhere on the world. It's correct to 5 decimal places, which is better than the Greeks knew, which was really incredible at the time. And the other thing he does is he states Pythagoras' theorem, the theorem we call Pythagoras' theorem, and has the version there in the 9 chapters is actually the earliest written statement of that theorem that we know anywhere on the planet. So the fact that we call it Pythagoras' theorem is a bit off, in my opinion.
Right.
At the very, maybe we should be naming it after Lu Wei, but also it's one that is kind of rediscovered all over the planet by many different people. And so the theorem in China is known as the Gaogu theorem, which kind of references the sides of a right-angled triangle. Of course, Pythagoras' theorem, just in case you've forgotten, is the one that's the sum of the square of the 2 sides of a right-angled triangle is equal to the square of the hypotenuse, the longest side. And so my view is that Pythagoras' theorem, that name, just gives it the wrong credit. It's like so many things in mathematics, it suggests that the Greeks came up with this thousands of years ago and we're all living in the Greek world now. But actually, Pythagoras' theorem, the Gaogu theorem, has been discovered all over the world. And if we wanted to give primacy to anyone, it should be these mathematicians in China.
This Pythagoras theorem does not cross my paths daily, but I remember this because in school it was drilled into us that according to Pythagoras theorem we had to solve some, and after 25 years after I passed out, I realized that he wasn't the first discoverer of the theorem at all then.
No, that's right. I think another interesting thing about that period and just the way we view the Greeks is that often we think of them as like cold, hard, logical people. And when we're talking about mathematics in other parts of the world, we entwine it with mysticism and divination and cultural religious ideas. And it's absolutely true that in other parts of the world that it was extremely based on culture and divination and religion and all of those things. Mathematics was entwined. But so too was it the case in ancient Greece as well. The Greeks really revered certain numbers over others because they gave them kind of divine importance. They also some ideas like zero, for example. There were early Greek mathematicians who kind of hit upon the idea of zero, but they couldn't really get to it because of their beliefs about what was important in mathematics and what was not, which was entirely religion, divination, culturally based. Even Plato said geometry will draw the soul towards truth, so it was really ideas that mathematics was this kind of tool for getting you closer to God in some way, or the gods in some way. And that's what drove their logic. They wanted to understand more about the world, and they thought that numbers had some pure divine element to them. And so by studying these whole numbers in particular, they thought that's how they would get closer to their gods.
And some of it was also pure practical in nature. I think it was it Maya civilization you write about, that is 2600 BCE. They were interested in astronomy because they wanted to look at crop yields just to make sure that they harvest their crops at the right time. They sow their seeds depending on, I think, sunlight perhaps. And sometimes those numbers can also be quite practical.
Yeah, that's right. I think from a long time ago, as you just said, people were associating with the stars, so much. So it doesn't have to be mathematicians, but many people trying to observe the sky, and they would like to calculate or find the patterns, right? So it was very ancient practice as well. Then we have like those tools, from Mayan times, and, there are more civilizations trying to figure out what's happening, outside of the world. And I think that's really interesting to include, because math becomes pure math, that it will, usually associate with like pen and paper, and also like, some great, mathematicians. But those people who are looking at the stars, they are sometimes, professional astronomer, but at the same time, they could be priests, or they could be like some commoners. They are trying to figure out, calculation of the movement of the stars. So I think those practical things really becomes like important parts of our world. So astronomy, it was like really a big part of it. And that's why we have the astronomy bits on the cover. So
yeah, I just want to give you a couple of numbers from the Mayan mathematician time. Just quickly getting them up on my computer, because they completely blow my mind about how accurate their mathematics was. And as you say, this is kind of starting 2600 BC, so thousands and thousands of years ago. And as you say, for practical reasons, they were extremely interested in astronomy. And so they became really, really good at it. And one of the things they were able to do was they calculated the length of a lunar month, how long it takes for the moon to rotate around the Earth. And so their calculation was that it was 29.5302 days. And today's calculation, our best guess using, all the telescopes we have, the satellites, everything, is 29.5306. So that only difference there is from 02 to 06. You think that's the best part of 4,000 years ago they came up with that. And then one more number of a similar vein is they also calculated how long a year is. Of course, a year is how long it takes Earth to travel around the sun. It's quite a complicated thing to actually work out how long that takes, because how do you know where you are in space, especially when you're sitting on Earth in South America? And the Maya calculation was that an Earth year is 365.242 days. And today we know that this is 365.242198. So really, only once you get to this fourth decimal point do you see a slight improvement on the Maya mathematicians' calculations. And that's without, we've been off Earth And that's how close the Maya were from sitting from their point on the planet. Absolutely amazing, I think.
If only there were lobbyists for mathematicians back in the day, that let's listen to these savants or scholars, and let's base our decisions on them rather than politicians deciding. But that's just the way it goes even today. And those decimal numbers, that is really one of those mind-blowing things, where without calculations, without atomic clocks, without the technology back in the day, we haven't been able to improve on some of those calculations even today then.
Yeah, that's right.
Something.
And even you say, those decimal numbers. A decimal is an amazing number system that is really easy to use and simple. But that's not what the Maya were using. Maya had a completely different number system, and those early number systems are much more complicated. They're kind of harder to do calculations with. Obviously a famous early number system many people know of is the Roman numerals. And if you think about adding together a sum with Roman numerals or working out a multiplication, it's just extremely complicated. So for you to use one of these early systems and come up with estimates for pi or how long it takes for the moon to rotate is just, to get that level of accuracy is really impressive.
You just took me back to school. There used to be a test for Roman numerals, and we would dread that day because we would be asked to write, 10,027 in Roman numerals, and you had to really remember. But yeah, that didn't come as easily as simple 1 to 9 and 10. Is simplicity a very important aspect of mathematics, where you've got 9 digits, 10 digits?
Interesting idea. Maybe precision, maybe not so much as simplification, but maybe precision was becoming like, a little more of, targets for mathematicians. But also what I see from the development of mathematics is more like, widening the view. So precision is not just one of the, aspect of it, but I think, by extending, like imagination that you started off, like you just go into a new world, new areas, and new ways of thinking about things. And I think that's how mathematics is developing. So Tim, do you see it differently?
I think that is right. But I do also think that the fact that these ideas are often expressed in different ways in different cultures, but then the amount with which they're able to run with them, I think the language that we use about them, and also the mathematical language, the number system and the ways that we can write them, also matters. And the fact that we're able to develop mathematics so successfully today, I think, is linked to those early pioneers who were working out what is the best way to write down numbers, what is a simple way to do that so that it makes sense and you can calculate with it. At one point in the book, we talk about how the kind of Indo-Arabic numerals that we use today came about. And they came about effectively from frustrations with some of the number systems that went before. Numbers tended to be very pictorial. They weren't yet decimal, which means that rather than having being able to combine 2 and the number 0 to create 20, often there would be a specific symbol for 20, there'd be a specific symbol for 30, a specific symbol for 40, and so on. And that actually meant that many early mathematicians, they couldn't write very big numbers down because they didn't have a letter or a numeral for them, because you couldn't just add zeros to the end. That wasn't a way of putting together numbers. So instead you had to invent a new number. And so Greek mathematicians, for example, very rarely wrote anything beyond 10,000 because they didn't have the right system for it. They didn't have the right way to do it. But then there, again, a kind of cultural element to it, that there was Jain mathematicians in the kind of Indian area around that kind of 6th, 7th, 8th century. They were extremely interested in very, very large numbers. And that was a kind of cultural pressure to be interested in those big numbers based on their beliefs. And that tweaked the mathematics. They kind of worked out ways to express really, really big numbers. And then later on, people like Aryabhata and Brahmagupta, they built on this to actually build a system where big numbers were better expressed. And those numbers are ultimately the numerals that we end up using today.
And guess what? I'm going to look good in front of my relatives and family members. I'll tell you why. I am Jain, and I had no idea that all this goes back to, some of the trivia that, working with large numbers, and there is, history associated with religion and mathematics. Although I'm sure my elder relatives would know this and they'll put me in my place that you should have known these things. But that was interesting, where religion
Yeah.
also plays a very crucial role for mathematics. And was it not Ramanuja who his calculations were based on instincts and a lot of religion, also influenced by religion, if I'm getting that right?
Yeah, I think there are many stories about him, hearing about, the concepts or things from like the time when he was praying, for example. So, Tim, do you have anything to add to Ramanujan?
Yeah, I mean, he's one of those mathematicians that has kind of developed a bit of a mythical status, I think, just because of the way he practiced mathematics seems so different to many other people. He was this mathematician that had very little training at all, and as he was kind of developing as a mathematician effectively on his own, he wrote this famous letter to Hardy in the UK and said, look, here are some of my ideas, have a look at them. And Hardy instantly recognized like something really impressive there. There was lots of mathematics that was not like mathematics Hardy had come across. He just by the way these equations and ideas had come about, he believed that Ramanujan must have had a bigger theory kind of hiding behind it all, and so was like, come to England, we need to talk, we must meet, I need to know about this. And a thing I think Hardy and his longtime collaborator Littlewood found with Ramanujan is actually he did have lots of ideas behind it, but also he was a very intuitive mathematician. He would often say that these ideas kind of came to him via God. They would be extremely often almost in like a finished form. So rather than a lot of mathematicians would kind of work step by step and finally get to a conclusion, Ramanujan seemed to come with fully formed ideas that must have come from just an extreme amount of natural talent for mathematics, maybe the religious component too, and just a different way of thinking than other people had had. And that's what actually ultimately made them a very powerful trio, was that Ramanujan had these completely outlandish ideas. If you go and look at some of the equations that are now associated with Ramanujan, occasionally numbers appear that just you can't understand why that's in the equation. Where has it come from? It feels like it has been plucked out of thin air, yet is part of a fundamental relationship. In a kind of way that you have pi r squared is the area of a circle. You're kind of like, well, where does pi come from? With Ramanujan, I can't remember the number off the top of my head, but it would be like 4,285. Just in this fundamental equation about algebra, it just appears out of nowhere.
Yeah.
So he would come up with these wild ideas, and then Hardy and Littlewood would help kind of flesh out the underlying structure to them and principles that would then allow them to reach a broader audience, so that kind of other people could like almost as a translator in some ways could follow some of that natural gift that Ramanujan had, the logic that he put on paper.
You write that Ramanujan would get to the answer and Hardy and his colleague would fill the intermediate steps so that people will be able to understand how you got there.
Yeah, absolutely.
Before we wrap this one up, a very important bit that I learned was that of women mathematicians, and it appeared that over centuries, up until more recently, they would, to use a maths pun, against all odds is what they had to, whether it was Kowalewski, if I'm pronouncing her name right and not butchering her last name, back in 1850, or later Wang Zhengyi. Could you give a few examples of what you discovered and what were, although their struggles will not define their work in isolation, because what they brought to the table was far more, but they had it hard as compared to men back in the day, or even today for that matter?
Well, first of all, I think we did not discover them, but their stories have been written so many times. And I think, our job was to really express like what her life was like as closely as possible as her times. So this is like a difference that makes like we're probably not be able to claim that we discovered this person and that person, but try to gather that information. So as for Sophie, there are many interesting facts. Maybe Tim can follow this up a little bit. But I think for me, it was really interesting to follow like what she had to confront. And almost everything that, about her story was like really strong objection or like almost impossible sort of hurdle with like, her courage and also ability and also the support network. So in a way that it was like, if I were them, that, I were her, for example, that I would be like, giving up. But her story is like really, really, interesting and also inspiring for us to continue the journey. And I think that was the part that I'm like really still like, admiring this figure. And we were proud to have her as like the first female math professor of the world. Yeah, she is like really unforgettable person, being in this book. So Tim, would you like to add some surprising facts about Sophie, like how she got over maybe like, going to Germany from Russia?
Yeah, so Sophie Kovalevsky, one of the things she is known for is she won this very famous prize called the Prix Bourdin in France. And she won that for there had been this problem that some of the great European mathematicians had been trying to work on that they hadn't managed to crack it. And she came along and really opened it up. And it's this problem that she called her mathematical mermaid, to kind of give it this kind of mysticism. But it's the problem of a spinning top. So if you imagine one of those toys that you can spin on a table and they spin around for ages, mathematically, it's very difficult to describe those. So there's the simplest case where they're completely symmetrical and the center of gravity is right over the middle. And then there's the point where they're no longer symmetrical, and then there's the point where they're no longer symmetrical and the center of gravity is not over the point. And it's that final class that no mathematician had been able to actually discover before Sophie Kovalevsky came along, and she really cracked it. So an amazing mathematical development. But as you say, she did all of that despite a very difficult start to her mathematical career. So she grew up in Russia, and she had a father who was very anti-women doing mathematics. He thought it would be a shame on the family if he had a daughter who pursued mathematics. Yet she kept getting exposed to it in little ways through her life. So one of my favourite stories about her is when they first moved into this house in Russia. They were slowly decorating the different rooms, and then they came to wallpaper the study, and the wallpaper never arrived, by which, for the reason that Sophie describes as rustic laxity and characteristic Russian inertia. So a real kind of little dig at the people who were meant to deliver the wallpaper. Yeah. But so instead, they kind of in a creative upstart kind of way, they had these old notes from her father who had been in the military and studied mathematics. And so they just used these mathematical notes to wallpaper the walls. And there was some of the first time she got to really look at mathematics, and she was just transfixed, and that kind of made her really want to become a mathematician. When she became old enough that actually might become a possibility, she tried to go to study, and she wanted to leave her home, but her father said, no, you can't do that. So really the only way for her to escape at that time in Russia was for her to marry someone. And this quite dramatic episode happened where there was this kind of nihilist movement at the time, and this young nihilist called Vladimir comes into her life. And there's this idea of the time called a white marriage, basically a fictitious marriage that means the young women no longer have to stay with their fathers, and they can have the freedom to go out and maybe attend a university or get a job or go and do something else. And so Vladimir thinks, well, my good deed here is I'm going to have a white marriage. But initially, the plan is that he's going to marry Sophie's sister. But he then takes a liking to Sophie and ends up marrying her. And that's kind of the start of her journey. That gives her the freedom to go and study in St. Petersburg. Then she ends up going to Germany and settling in Berlin for a long time, where she meets the very famous Karl Weierstrass, who then becomes her kind of mentor. And that kickstarts her career and ultimately leads in her finding the mathematical mermaid and spending all of her time on.
And through it all, I think she had a few tragedies where did her husband commit suicide, if I remember that bit correctly. But in the end, when she became a professor, she wasn't paid because of discrimination, and then she had to scrounge money from the students who chipped in. But in the end, this is I think by far the favorite quote from the book. You quote her, and it says, "Say what you know, do what you must, and whatever will be, will be." After all of that, and after winning the 5,000 francs for cracking the mathematical mermaid problem, that says a lot about the character as well, and what characters these mathematicians were behind their geniuses.
Yeah, that quote was impressive and really summarizes how she felt about, going after mathematical mermaid for a long time. So you're right that this quote means so much, and not just, for her or for us, but for many people, like, who challenges many difficult situations. I think this is like really a good quote to remember. And also I was really struck by, the support, this is like more becoming like female mathematicians, being, going into the mainstream of the pure mathematics. And then after her point, there are more people to introduce in the book. So they become more rich in a sense, like, there are many, great figures, like either male or female. So I think, her really activities or her fame, started to shift the concept of the male mathematicians back then. And I think this is so great point of the history. And really, I praise Sophie for what she has done.
Yeah, one other quote from Sophie I'd just like to share with you is, as you say, there were many points in her career where effectively, if she'd have been a man, she would have been in a paid position, and she ended up getting something far, far less than that. Even just attending university, she was only allowed to audit some of the classes. She wasn't allowed to fully submit her thesis at the university she was at. So constantly she was given a lesser role for her compared to her abilities. And eventually she gets this position in Stockholm thanks to a friend. And when she arrives, she's like this sensation, a female maths professor. And a Stockholm newspaper describes her as a princess of science. And she sees this, and her response is to say, look at that, I've been made into a princess. It would have been better if they had given me a salary. Which I think is just like a perfect quote. She just is like kind of belittling this ridiculous way that they've described her as a princess, and just been like, all I'm asking for here is some kind of parity. I'm doing work that is perfectly... Well, she's doing absolutely fantastic work. But if she had been a far less talented man, she would have been receiving a paid position.
Yeah.
And instead, she's this kind of sensation, but also not really taken seriously at the same time, which is, I think her outlook on life really just helped her fight that from that quote that you say.
And is that changing now among these? Who are today's sensations?
That's a good question. I mean, so like one thing we try and do in the book is talk so much about how it's a collaboration, and so we actually don't spend very much time in the book looking at kind of today's rock stars as such. I mean, there are some out there, but I feel like calling them out might be a bit, I don't know, not quite in keeping with this idea that, especially today, mathematics is such a collaborative effort that there's many different people. And one metaphor we describe is that mathematics is kind of like a relay race. One person passes the baton to another person to another person. And often what happens is the last person who has the baton, when it crosses the line, gets all the credit. And instead, really, mathematics has become much more about people around the world coming together to collaborate on many, many ideas. And that's it's very rare now that you see a research paper that has got one name on it. Often there's many names on it. And I think that's a reflection that mathematics is a creative pursuit, like you mentioned, but it's also a team sport. And I think that's an idea we'd like to get across.
Lovely. Love that answer. Thank you again, Kate and Timothy, for your time on this podcast. It was lovely, and congratulations yet again on the book. And I wonder if do you think in school should mathematics be taught any differently? How is it in, say, Tokyo, in London, and I'll tell you how it is in Mumbai. It hasn't changed much when I was a kid. It's pretty much the same. Do you think it's time that maths be taught a little differently, or is it good enough? Or even the history of maths, should that be also be brought to fore, Pythagoras included?
Well, definitely, I would say that I would like the mathematical education to include the human stories, of like from many places of the world. So while learning mathematics, they can create an idea of mathematics as like a human endeavor, and it's also continuing. So there's no like 100 scores, there will be even more to do. And, what we need to teach is like, courage, and also like ability to sort of continue trying and so on. So I think those stories are going to help. So I will hope that many parts of the world trying to tell more stories about foreign researchers, or stories from ancient times, like how we started and how we associated with mathematics for a long time. Yeah, definitely. I would like to see more schools teaching a history of mathematics.
Yeah, I guess that the thing I would like to see change is I agree with everything Kate has said, but also that mathematics is not a memorization subject. It's not about just learning things and repeating them. It is a creative pursuit. It's an artistic pursuit in many ways. And I think that is, at least in UK school education, it's pretty removed from the curriculum. I think really what mathematics is a way of thinking. It's a way of building up an argument in a logical and rigorous way, and that is an amazing tool that applies to so many different things, different areas, different concepts, and also ideas outside of mathematics. And I think if we built that more into our education, that would give people such a fundamental and powerful tool, way beyond memorizing many different equations or relationships between triangles and circles and all of that kind of thing. Instead, it's about a powerful idea that you can use across your life.
Lovely. On that note, time to wrap this particular podcast up. Thanks yet again, both of you, for your time.
Thanks
from
for having
London
us.
and from Tokyo.
Thank you very much.
Thank you.